Once it's nighttime and it's a starry night, it's not a bad idea to gaze up at the stars. Did you know that the light that reaches our eyes from the stars have been traveling from the star for decades or even centuries? So whenever you gaze at the stars, you're looking back in time. And there are billions of stars in our galaxy and billions of galaxies in the universe. So how old is the universe? Or do we live in an eternal universe? Join us as we discover the age of the universe. Many scientists believe the universe was eternal and timeless. It had always existed and will always exist. This was conventional scientific thought until Lemaitre's work in the 1920s. Back then, in the golden age of physics, the Belgian priest Georges Lemaitre started to explore the idea of cosmology, eventually making a very interesting conclusion that proved to be indeed groundbreaking. But the foundation of his work was the observations of Edwin Hubble. Edwin Hubble looked at the light from galaxies far away from Earth and realized that the dark absorption lines showed greater red shifts. He concluded that distant galaxies had bigger red shifts because they were moving away faster. Light from further galaxies has traveled for a greater amount of time through an expanding universe. This increases its wavelength, giving a greater red shift. The greater the distance from Earth, the bigger the redshift of the absorption lines. Hubble used the redshift to calculate the velocities of galaxies against their distance from Earth. This means if the distance of the galaxy away from us doubles, so does its velocity away from its observer, called recessional velocity. As the recessional velocity increases with the distance of the galaxy, it implies that all the galaxies originated from a single point. In 1923, Hubble confirmed that many of the spiral nebulae that were detected by different scientists were not within the Milky Way. They were from distant galaxies millions of light years away. Just a few years after this announcement, Lemaitre observed an interesting pattern. Just as the original Hubble observations, he realized that for a lot of galaxies, the farther away they are, the more they expand. Lemaitre was an excellent mathematician and was able to accurately work it out. He concluded that if the universe was actually growing in size from a much smaller point in the past, all the observations from Edwin Hubble would suddenly make sense. In the process, he calculated some of the first values for what we now call Hubble constraints, although more officially, it's known as the Hubble-Lemaitre constant. Lemaitre then sent all of his observations and calculations to Einstein for peer review, but did not get the response that he hoped for. Einstein dismissed him, stating that, "Your calculations are correct, but your physics is abominable." What would have been quite the string, but it did not take very long for Einstein to be proven wrong on that point. The great physicist had to concede because Lemaitre had just discovered the idea behind the Big Bang. Soon enough, it became conventional that the universe is growing in size. In Albert Einstein's theory of relativity, time is woven together, with the three dimensions of space forming a bendy, four-dimensional space-time continuum like a bowling ball on a trampoline, encompassing the entire past, present, and future. Einstein's equations portray everything in the block universe as decided from the beginning. A few weeks before his death in 1955, Einstein wrote, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." Before 1999, astronomers had estimated that the age of the universe was between 7 and 20 billion years. So how did we measure the age of the universe? It's simple, reach for the stars. Astronomers have long discovered the relationship between observed properties of stars and their age. This is because a cloud of cold gas collapses under its own gravity, leading to the formation of a large number of new stars of different masses, colors, and brightness simultaneously. Once a large, bright blue star is observed, we know this star burns through its fuel first. Gravitational interactions between stars cause them to fly apart, but another reliable means of determining the age of the universe is the study of the interactions of matter and energy, beautifully expressed mathematically in Einstein's general relativity. This equation accounts for the amount of types of matter and energy present in the universe. There is another key factor that is expressed in Einstein's work, the speed of the expansion of the universe. So if we trace the events backwards like an archaeologist would, we can reliably conclude that the universe is not younger than 12 billion years. If the astronomers who estimate that the inverse of the Hubble constant is as small as 10 billion years are correct, then the age of the universe will be less than the age of the oldest star. That would be the same as saying a child can be older than his mother. This contradiction implies that either the Big Bang theory is incorrect and we need to modify the theory of general relativity, or that we need to change our beliefs about stellar evolution. For a more precise figure, we would look at the elegant Friedmann equations derived by Alexander Friedmann in 1922. The Friedmann equations describe how matter and energy affect how spacetime bends, embodying the very essence of the Einstein equation that makes it clear that it's not only matter that produces curvature, but any sort of energy. Thanks to advancements in technology this century, measurements made by NASA's WMAP spacecraft showed that the universe is 13.7 billion years old, give or take about 130,000 years. They were able to do this by making detailed observations of the fluctuations in the cosmic microwave background and using that information in Einstein's theory of general relativity to run the clock backwards to point zero, the Big Bang. So, when observing the abundance of light elements like hydrogen and galaxy clusters, collisions, supernovae, and even cosmic microwave background fluctuations, it all points to the composition of the universe and how it all expands. In contrast to our intuition, the universe is actually made up of mostly dark energy, 27% dark matter, just 4.9% of matter as we know it, while neutrinos, photons, spatial curvature, cosmic strings, and other exotic components barely make up 0.5% of the universe. At this point, we might assume it all depends on the expansion rate, but the best data that has been collected in the past 20 years comes from the cosmic microwave background radiation, or the CMBR for short. CMBR is another piece of evidence that shows the expansion of space, supporting the Big Bang model of the origin of the universe. The short wavelengths of the gamma radiation emitted by the initial explosion are believed to have become stretched due to the expansion of space into longer wavelength microwaves. Those values have all converged on the same expansion rate, 68 km per second per MPC, with an uncertainty of just 1 to 2%. When you calculate what that means for the age of the universe, what you get is precisely 13.7 billion years. This is completely consistent with everything we know about stars. So, as far as the age of the universe is concerned, this is a slam dunk. Certainly, we don't know all that we should know about our universe, and there are many unveiled mysteries that will most likely pull the carpet from under our feet. We don't know how fast the universe is expanding. All we have are speculations and hypotheses. We don't know why different methods of measuring the expansion rate differ by such an unexpectedly wide margin. We don't know what dark matter or dark energy really are. How valid is general relativity on the largest of cosmic scales? Hard to say. How much of the universe is obscured in the form of dark matter or dark energy? Is it more dark matter or more dark energy? Currently, we have no idea. There are so many uncertainties that are quite significant. Discovery of the answers might permanently reshape our view of the cosmos, but till then, we stick to the most satisfactory explanation we have. The universe is not timeless, but has a definite point of origin. Why it all began is a matter of philosophy, not science. But that would be another video. Thanks for watching this video. Don't forget to smash the like button, share our video with your friends and family, and subscribe to our YouTube channel for more amazing content. See you on the next one. Until then, bye.